I just kind of want to make a quick little video about inductors. Um, I've got this Falstad circuit I created here. It's just a 1 Henry inductor. It's a 50-volt battery. You can see what the values are. Now, this right here is a 200 volt and a 12 volt Xfmr diode, and I don't really care about how everything's ideal on here. Just try to represent, look at some of the ideal properties of inductors, really. So, I've got this rigged up. You can see a series of switches here, and this is a typical, arrangement you would see in an inductor. And let me try to change the scale of this real quick on the horizontal axis. Let's see, so it slows it down quite a bit. And now let's go ahead and flip it, so that we charge it up directly from the voltage source. And what I'm going to demonstrate here is that when you're charging an inductor, if it's from a constant voltage source, it'll be a linear charge curve. So, and let me speed the simulation up a little bit here. So, but the thing about it is that its current will not be bound by anything. So it'll keep charging up to infinity. Now, of course, in a real coil, you would have real coil resistance, okay, which would actually act like a limit to the current. But right now, I can go up to like, 30 amps here, and in fact, we can keep going. 40, 50, it goes right off the scale. So there's nothing limiting it. Now, what I'm going to do next is I'm going to go ahead and, it's a 1 Henry inductor, all right, and it's, storing energy in it. So let's go ahead and change the discharge through this 12 volt Xfmr here, because this is a 50 volt supply we charged it at, and you can kind of see how long we charged it for. Okay, what the time step was, because I think it's like 20 milliseconds per division. What the hell was the time step on it? I wasn't paying attention to it. It's 100 milliseconds per division, right? Alright, so we kind of stopped it somewhere over here. So, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Over 10 divisions, so so that's at least a second right there. So we charged it for a second. Now note how long it takes to discharge it through 12 volts. And this, I'm going to do the same test again more properly here in a minute. Alright, so we got 60 amps. Alright, now we're discharging it. Now note the voltage and the current across it. See, it switched to minus 12 volts because the inductor's polarity is reversed. So you can see its voltage has dropped down here, and here's our zero line right there. Let's see how long it takes this thing to discharge. And note too, that's why I'm using a Xfmr diode, because it's discharging as a constant voltage. So it's going to be a linear discharge curve as well as a charge curve. But look how much longer it's taking to discharge than it took to charge. So, quite a big difference right there. Now we're finally about discharged, and then the voltage goes away. So you get that interesting, sort of square wave pattern, because you charged it with a constant voltage, and right up until, it lost all its power, it still maintained that voltage more or less, and then all of a sudden it flipped to zero. So it's just an interesting property of inductors that they do things like that. Now let's go ahead and charge it up with a resistor, and you can see the classic charge curve on this. So let me go ahead and switch it over and speed up the display. Alright, you'll see here the voltage is not constant, it's changing, and in a curve similar, but in the inverse, more or less, of the charge curve. So by the time when the voltage drops to zero, eventually, the inductor's field is fully charged. We got a constant 25 amp current going through it, and 25 amp is the actual current. You can see the voltage keeps falling and falling and falling. But you can see, what the shape of that curve is. But now let's flip it over and see how long it takes this to discharge, because it only goes up to 25 amps. But so we charged it non-linearly, but we're discharging it linearly. So it's got a linear current curve on it. So its voltage still behaves the same way. So let's go ahead and charge that sucker back up again, and but like I said, still it took longer to discharge it than to charge it, as you can see here. Because it's essentially fully charged, here. But we charged it at 50 volts, but because it went through a resistor, it takes a lot longer to charge it, than it would if we charged it with no resistor. And I'll do that next just to show you. But like I said, since we're discharging it at 12 volts, it actually takes longer to discharge than it will at 50 volts. I'll try to stop it at 25 amps. So I got to manually stop it. Whoops. Okay, messed it up. Damn it. Stupid Falstad. Okay. Alright, 25 amps, that's how long it took to charge up, but looks at how long it charged up linearly, but now it's taken several times longer. In fact, it's taken longer in proportion to the voltage difference. So, that's how fast it charged, at 50 volts, but, at 12 volts, which is it took over 4 times longer to discharge, basically. So there's a definite relationship there between discharge voltage and versus charge voltage and the time differences. So, if these were identical, like if I had this at 50 volts, it would take just as long to charge as discharge, and it would be linear if it was going through a Xfmr diode. Now, of course, in practice, you need some awfully big Xfmr diodes and stuff, and just demonstrating an example. There's a lot of practical, don't try to build this circuit, doing what it's doing. But it just demonstrates the principles involved. And anyway, to get back, I'll go ahead and charge it up this way. Alright, so we quickly charge it up. Alright, we're almost there. So let me go ahead and show you what happens when you remember this was like a 100 volt Xfmr, right? So it's like twice the voltage. So let's see what happens. Very interesting, huh? The discharge time was really, really quick. Alright, so, because the inductor is basically trying to maintain its current flow, but it can't. So it generates a very large voltage, and you'd see, if I slowed it way down, you would see that it's like 100 volts that it's discharging at. So let me get it up there. Alright, that's close enough. So I got it way slowed down now. Alright, so you can see it's actually minus 200 volts. So I guess that's what I had it set to, is 200 volts. So yeah, it's discharging at 200 volts, but it'll do that really quickly because it's got the same amount of energy. It's trying to maintain the same current. It's still at 24 amps, but it doesn't take long for that to drop. So it'll drop precipitously. As you can see, but it'll stay at 200 volts, until it basically is fully discharged. Its magnetic field. It's linearly discharging, because again, in a real world coil, it wouldn't work this way exactly, but you can come close. If you had sufficiently low resistance and so forth. But at any rate, the fact of the matter is that, okay, it discharged at a much higher voltage, but very quickly. Alright, now let's switch it over to a 200 ohm resistor, and let's see what that does. Let me charge it up quickly. Like I did before. It's hard to stop this thing on a dime. Okay, it's close enough. Alright, so now let's go ahead and switch it into discharge. Now 5.3 kilovolts. Okay, we charge, we can charge it with 2 ohms and discharge it with 200 ohms. See, at 2 ohms, if you recall, it got up to 25 amps maximum. Well, at 200 ohms, it's still got the 26 amps flowing through it, but it's actually upped its voltage, to 5 kilovolts, about 100 times what it would have been over here. And let me go ahead and run this thing fast so you can see how fast it discharged. Now let me go ahead and switch it back over to resistor and get it charging. I want to discuss this. But you can see that it generated a 5 kilovolt pulse, but it discharged it really quickly. Again, its current never exceeded the original 26 amps or whatever we had it at, but it's the voltage made it really discharge really fast and linear, non-linearly, because this is a non-linear discharge. But anyway, here we're charging at 2 amps, so you can see how long it's taken. It takes quite a bit to charge it up, right? Now let me slow this down before I flip the switch. So let's go ahead and flip the switch. Now we're at 4.9 kilovolts, but still at 24 amps and falling. So, but now it's going to be a non-linear discharge curve because we got it on a resistor instead of a fixed voltage source or voltage sink like a Xfmr in this case. Okay, let's speed it up a tad, but you can see what's going on here. I mean, yeah, it's generating quite a bit of voltage. So, and that the current falls very, very rapidly compared to what we charged at. No comparison. See, I mean, it's actually a non-linear discharge curve. It's so quick it's hard to even see, but it is non-linear just like it was. So basically, the rule is that we charged it to 50 volts through this resistor, right? So, but we discharged it, at 5 kilovolts, okay, through this, which happens to be 100 times 50 volts. So because this resistance is 200 ohms and this is 2 ohms, it's 100 times difference between the two. It discharged at 100 times the voltage, but in 1/100th the time. You kind of find out if you kind of did the math. It discharged a lot quicker than you charged it. So that's in essence how inductors more or less work, and the little magic trick they do by switching polarity, is clearly demonstrated as well. Now, there's another little interesting facet if you actually take this concept and apply it to a transformer. And I have not verified this, but this is something I've been wondering about for a long time, and the results I'm getting on the simulator are tantalizing. I will try this at some point to verify its truth. But basically, yeah, we got kind of the same basic circuit. In fact, I cobbled this together based on the previous circuit we were playing with. But let's get this thing charged up. Now this is, these are the specifications. Turns ratio 10, primary inductance 1 Henry, which is what we're dealing with in the other circuit. And, I got the same 2 ohms and so forth. But I've gotten rid of all the discharge circuitry. So, and you can see we're about up to full charge now. And you'll note that I've got a 1K resistor on the secondary of this transformer and a voltmeter across it. So, technically, this isn't like, most simulators, don't like this kind of thing. But I believe the results are accurate. Because, I've always been curious about this because I was like, okay, when you open a switch on a real transformer, you get a spark, right? Even if it doesn't have a load in it, you'll get an arc. And, but I was like, well, if you had a load on a transistor, and you opened the primary circuit, shouldn't current flow in the secondary if there was a load on it? Instead of arcing on your primary, you would think it would. why should it just arc on your primary? Because again, the thing's trying to continue its current. So just like when I flipped the switch on the previous demonstration circuit, you can see how the voltage shot way up. Well, that's what ultimately generates an arc. If you're opening a switch contact, it's trying to generate whatever voltage it needs to maintain that current. But it just occurred to me a long time ago, I mean, that shouldn't be the case. It shouldn't have anything to do with current. It should be about maintaining its flux. I mean, it's just incidental that it's trying to maintain its current flow. And in a single inductor, that's by all appearance is what it's doing. But in theory, it doesn't want its flux to change. And as long as you got a current flowing through it, like a DC current like we have now, well, it should stay, it should be happy-go-lucky. But boy, once you try to remove that voltage, well, it doesn't like that, so it tries to maintain its current. It flips its polarity to do it, but it's really trying to maintain its field. And my question was, well, this is a transformer, right? So wouldn't it try to discharge through the secondary if you had a secondary load on it? And the answer is yes. And apparently there's good cause to believe that's true, because apparently, yes, if you open a switch on the primary of your transformer, it can damage what's on the secondary because of that high voltage arc. If you're just opening it up with no snubber or anything on the on your switch, I mean, yeah, that can actually cause damage if you don't have some kind of some kind of protection on it or something. And oftentimes, most of the time, a filter cap is plenty of protection, right? So, you usually won't damage your electronics or anything because, you usually have a filter circuit, bridge rectifier, all that stuff. But I'm saying, if you had something sensitive on there that, was some kind of component that couldn't handle some kind of a surge, it could possibly get damaged. It's actually something to be aware of. And that's what I'm going to demonstrate here is that, basically I have this thing configured as a, more or less a 12 volt transformer. You can think of it as a 10-to-1 windings ratio. So, you can see what our primary current is here, right? And I got the thing fully charged up. And I've got a 1K load resistor on it, right? And again, in real life, you wouldn't want to build this circuit. And you'll see why in a second. Because this is taking things to extreme. We are dealing with ideal components. So I'm going to open the switch here and look at what just happened. Saw that 74 kilovolts, right? And this happened in such a quick flash, even on slow motion. It didn't catch it. I mean, it just happened super duper fast, because of, how much voltage it's generating. So, earlier I had these two back-to-back TVS diodes, that's how I initially did this test, and, of course that keeps the voltage more constrained. I'll put those in play here in a second. Let's see. Let's see. I'm going to get this thing charged up here. I could do it just the other way, but alright, about to charge. Alright, so I'm going to slow this motherfucker real far down. So, I'll just go ahead and do it now. Alright, so you can see, we're at 159 kilovolts, 159 amps. Remember, we're only at 24 amps on the primary, but since we got that 10-to-1 ratio, it amplifies the current too. So, it's trying to, it wanted to maintain 25 amps on the primary, but the only thing it's got a load on is the secondary. So, so of course, it's generating, a 10-time multiple in current too, basically, even though this thing's wigging out because of just the, just everything involved in it. It's not really looking at it quite right, but the fact of the matter is, it shows the principle that it's generating super high voltages. Again, in reality, it wouldn't do this. I mean, it'd burn your windings out. I mean, it would just arc your switch before it would actually do this. But the fact of the matter is that it shows you that you can generate not only a high voltage but a super high current with this kind of configuration. So I mean, it could really zap something, but its discharge, the discharge time is not only shortened because it's got this super high voltage on it like before, but it's also got a super high current now too. So that's interesting. So overall it helps it get rid of its current. But if you think about it, it makes sense because you got fewer windings on the secondary. You're trying to maintain a primary current of 25 amps. Well, the secondary's got fewer turns, so if it's going to maintain any kind of a field like that, it would have to have 10 times the current, of course. But because we have a high impedance load on it, it's got to do that not only at high current but at high voltage. These are impossibly high, but you get the idea. So now these things, I think I had set at a couple of 100 volts. So let me go ahead and reset the thing just for shits and giggles. Let's get this thing charged up fast. Okay, I'll take it at like 10 amps so you can show a little more practical. There we go, 10 amps. Okay, now let's see what happens with these diodes. Now let's check what these were first. Okay, they're 100 volts, so it's going to discharge at about 100 volts. We charged it at 50 volts, but it'll discharge at about 100 volts. But you'll see what happens, say it's minus 101 volts, but at 100 amps, we just charge it up to 10 amps, right? So let's see, speed this thing up, and you can see how short this was. Not nearly as short as the last one, but it was just at 100 volts, but it still discharged extremely quickly. So, pretty much at 0 amps now. Again, I don't know if this is simulating. I can't attest for this because I haven't actually done this yet, but I'm going to try it because in theory it logically should work. So, that's the question mark, is because you'd have to scale everything way the hell down to do it with a real transformer and everything. Because you got to understand, real transformer, like let's say you use a 300 VA transformer, for at 60 hertz frequency, it would have to supply 300 joules per second, right, to a load. That's its capacity. But really it's only supplying that you got to divide by 60 basically. So in one waveform, because again, if it's just a pure resistive load like we had before, yeah, I mean it's going to be supplying that in 1/60th of a second. It's supplying 300 divided by 60, which is like 5 joules per cycle, just as a rough rule of thumb. So so you got to kind of like watch what kind of current you apply to this and everything, because it's not going to be maybe what you think. So I don't even know if you wanted to put, would want to put 1 amp through the primary since it's DC. But, that's how I would do it. If I were doing this as a real transformer, I might, use like a 10 volt power supply. Preferably, one that's not electronic, just to be safe, maybe. It'll probably be fine as long as you're charging up with a resistor. But, the point is to get it up to like 1/10 of an amp or something like that. And because in theory, any transformer will do this, no matter what its size. You just got to be careful what you put in the primary, because you are dealing with DC, and you can actually really easily saturate your core at, putting DC through one of these transformers, apparently. So, from what I hear, so it's something to be cautious of. It makes me wonder. Just be cautious. You don't want to. Because it's not going to do you any good to drive the core into saturation, and I'm not really sure how much current it takes. Because, like I said, you think, well, geez, if it's a 10 amp secondary transformer, it may, take that 1 amp on the primary. But again, with DC, that may not be the case, because remember, the voltage is constantly changing. So it's just something, just be cautious, when you're doing that, because otherwise you might, well, get bogus results at the very least. Because it would probably take 1 amp of current, I'm sure, if it was a 300 VA transformer. Probably take 1 amp of current on the primary, but, and if the secondary is rated at 10 amps, you're probably fine to try it. It's just, you may saturate your core sooner than you think, I don't know. So, I haven't investigated that enough, because I don't usually use transformers, with DC signals, right? So I've never actually experimented with any of these on that level. The only thing I found out when I was a kid is that if you hook a inductance meter up to a transformer, all right, and you put a potentiometer on the secondary, you can actually measure, change the LCR measurement, by changing the pot. I don't know how much of the actual inductance you're changing, because again, it's it was in DC though. I mean, I was measuring it with an LCR meter, so who knows? They probably had some test frequency in there, but I don't know that you were actually making a variable inductor, but it was always intriguing. But it's really reflecting the pot, from the secondary to the primary, and but what that's actually doing to the inductance, because the inductance tends to go away on a transformer once you actually start loading it, like with a resistive load, for example. So it quickly goes away. I mean, the transformer, draws low current when it's unloaded, mostly because it's got a huge inductance. Typically, it's not unusual to see a main, like a 300 VA transformer to have like 50 henries of, inductance, and that means it's going to have a big reactance. So it's just something to watch out. But at any rate, my point is, take suitable precautions if you wanted to try this yourself. Because again, I'm going to do it myself too. I'll probably make a video of it if and when I get around to it. But at any rate, it's a very curious phenomenon. And I assume they use something like this when in like PC switch mode power supplies that have those little step down transformers in them that are, high frequency or whatnot. But again, yeah, you could probably try it out, because I intend to at some point. 10 amps, okay. Alright, so let's open that circuit, and, okay, now it's only 11 volts, but hopefully the discharge time will be longer. But still, the current is 107 amps, so it's still going to discharge pretty darn fast. But again, it's a constant voltage discharge, so you can see the current's falling and falling and falling, so it should be linear. But like I said, I don't think, let's see, yeah, but see, I'm not graphing, you got to understand this, you're not seeing this current flow, on the graph, because it's monitoring this. Like I said, I could actually see if it'll graph what's going on here. Let me see. I don't know. I'll just try to do it with this one. And dock scope. Alright. Okay. So let's go ahead and charge this sucker up again to 10 amps. Okay, good enough. Now let's go ahead and open the switch and see what happens. Alright, yeah, how quickly it starts. Because like I said, I don't know if this thing's simulated, because you're not really, I'm not really doing this properly, and I don't really know honestly how you would simulate that, particularly in Falstad. But it's you're really not seeing the current waveform properly, because you can see what it's doing on the meter, and again, I do believe that's fairly correct, but the scope isn't. I mean, it's not, it doesn't have anything to reference against, and that's why it's creating a problem, because it doesn't know what to reference. I don't know if you could just put a ground here, but I tried connecting this secondary over here, and it really just, didn't care for that much. But at any rate, but the point is that I do think this theory is valid. And I think what's going on here with the meters is a reasonable expectation of what would happen in real life, because it will, if you just suddenly open a switch on the primary and you have a load on the secondary, it will actually try to eat up some of that. But it does depend. It still may try to throw an arc too, depending on how your circuit's set up and how much of a load you're actually using, etc. So, but at any rate, it's just interesting, curious aspects of inductors that warrant some further investigation. So anyway, cheers.